cleaning.
So now it's sugars.
Yeah, I clean them right up. Look at that. This is so coarse.
Because that was what we voted upon.
It's also thoroughly used.
Well, yeah, I wouldn't want to put that anywhere near my
That makes
face.
no sense.
What do you
But it
use
works
that
for like paintballing and airsoft guns and masks.
Well, yeah.
Hey, question. How much of this sugar section is actually on the biochem test?
None.
None? I was just double
No,
checking.
that whole chapter is not on the test.
I'm so confused by his ways.
Well, everybody voted. I voted against that. I wanted everything to be on this test, so that he couldn't be very specific. Now you can go as specific as he wants, and it was like 2 chapters. It's gonna be off.
Well, he already, like, is it, are we on, was that the 6th or 7th quiz?
I don't know, but I didn't do very well. I wasn't.
You
there.
get 2 drops now.
I need like 3. To be honest with you, those quizzes are hard.
I've been getting 8s actually on them. I don't know.
I don't study anything. I only study before the test. It's just memorization.
He's probably going to add another 4 or 5 quizzes.
I
Let's be
hope so.
honest. Well, because
Only if he has drops.
the last time he had it in drop, so.
And my app didn't work on my phone very well for the first few quizzes, so I lost a couple points at the beginning because it wouldn't like load the class right away. And so I was like down to like 6. Hate that class.
Everyone does. It's a biochem.
A waste of time just to sit there and memorize.
No one likes biochemistry. Wait, there's no biochemists in here, are there? They shouldn't be, but I'm just double checking.
Yeah, didn't you know it's one of Lyman's like 5?
Yeah.
Yeah, I was about to say that.
Going to the biochem too.
At this point, I should just figure you were in it.
This is not due today, this is due Wednesday.
See.
Wait, this Wednesday?
Yes.
Yes.
Good, because we have Veterans Day Saturday, so we had that Friday off, so then it's.
It's okay, it doesn't look super good.
This Friday.
That's what you get for having 3 majors, 10 minors, and a master's.
I had 2 majors, a minor, and lots of other random.
2 other not quite minors. Because I don't want to be in school that long.
Well, I mean, you're already going to be like a super deluxe senior at this
Right.
point.
Alright, so
Sounds
if
like
you've taken 5 years of school minus a semester, so 4.5.
Well, I mean, he's already at
You
super
would take
senior stage, so.
1 more
you know.
year. So you'll be at 5.5?
Shoot, super squared
sounds so
senior. Is that better?
Yeah, I think it's gonna end up being 6 years.
So, wait, if this is your 5th year,
So I feel like we might
this is
go.
the first semester of your 5th year, with a semester off in between there.
Given we just calculated out.
Well, that wouldn't matter, right? Because okay, so like I definitely got to be past like 4 years, so
Well, there's one that's
Even with
seven.
that drop semester?
I think so.
Sure,
Yeah.
so.
Well, because I graduated
It's probably
2012 from high
We're
school.
getting some of those.
Took a year off, played concrete, had oral surgery, all that shit.
Yeah.
Got West Nile since I started next year. Yeah, done goofed.
Okay, the system doesn't cooperate today, so I'm not sure if I will be able to write. So it limits us only to pre-made writings. Physical chemistry, observables for experiment, quantum theory, oscillator. Our wish is propagate and predict future, right? And we suffer a lot of boring math for this. What will be non-boring, hopefully very soon, is individual research projects, where you practice the same code as we did recently, with remaining meetings on Wednesday. We will pick up a couple of additional skills, including last time we were learning how to set up an observable for transmission probability, which will be also useful for quantifying the reaction yield. Another thing that we need to do is to process this transmission probability. If you were not attending this meeting, it was we split our one-dimensional space on 2 parts, left and right, before reaction and after reaction, and we integrate what was here and there. And then if the wave packet comes to the region that corresponds to products, the yield of reaction raises versus time. Right? Can be 0, can come to 100%. And what we didn't do yet, in addition to reaction yield, how many percent, one may want to set up the reaction rate, how quick does it go, or very, very slow. Basically, it's just feeding this function to, let's say, exponential or something, whatever, and getting that constant. But you will need to do it by hand. Your projects, I plan to give options to choose, but you may start thinking creatively. Most of the projects will be selecting area of your scientific interest, problem like charge transfer, electrochemistry, reaction with activation behavior, and projecting the problem that you're interested on to one dimension. Do not panic if you cannot do it next second. We can discuss. I will throw in some ideas, but just set up a little seed of thoughts. Project problem of your interest onto one dimension. In vast majority of problems, it is possible. So now for oscillations. Okay, homework, because to celebrate Veterans Day, we bring homework earlier. So what do we remember from last time? The practical operations, working theory, are almost never done in true space, in space of continuous functions. Most of calculations and operations are done in discrete space of selected bases. In the majority of problems, the basis is chosen to be eigenstates of some well-defined problem. Right now, we are so lucky that our problem, quantized oscillator, and base set are coinciding. So cat 0 means ground state of oscillator, cat 1 means first excited, cat 2 means what? Cat 2, it's the KET, second excited state. We introduced raising and lowering operators, and they correspond to transition between nearest neighbors. If it is going up, it yields a factor square root of n plus 1. If it goes down, square root of n. If we multiply creation by annihilation and practice a little fun of operator algebra, we see that it will correspond to diagonal operator. Okay. No, I'll better not show it here. Otherwise, it will do strange things. It has this option of writing, but when when you have a rifle that you never tried, the line where the bullet will come and the line where you target do not coincide. So I pick one place and it may mark on another side. So it will be strange things if I keep trying. And if we express Hamiltonian as product of creation and annihilation, we see it has only diagonal elements non-zero and off diagonals are zeros, which is kind of expected. If we have eigenfunctions of the Hamiltonian, that Hamiltonian doesn't change them. Any eigenfunction affected by Hamiltonian is projected onto itself, multiplied by eigenenergy, right? So it goes along with what we defined before. I'm going to spend about 20 minutes for nothing, for a thing that you can do yourself easily and you can imagine. It is just repeating of the last slide, but for the sake of homework and your comfort, like maybe through doing a trivial thing, I will cover some minor things that will be a surprise for you, or you will cover some white spots. So it will be normal if next 20 minutes you do not record anything, you do not find anything new, it will be a good sign. But you may find something of the story on the board, you will cover white spots. So, what is the eigenvalue of Hamiltonian operator for ground state of harmonic oscillator? What is the energy of lowest state, if you know the frequency of the oscillator?
1/2 h bar omega.
Okay, you are ready to answer it in the midnight. Everyone agrees with this, right? So the ground state energy in classical mechanics, when there is no energy, if it is in the minimal equilibrium point, the energy is zero, corresponds to minimum point of the potential. In quantum systems, quantum vibrations, there is a 0 point energy, which is half of vibrational frequency, right? So it is not a surprise for you. You have heard it before, right? How can we connect this information of the eigenvalue of energy with all operator garbage that we did before? It should be consistent, and logically we can derive it out of there. Okay. Remember, in the Dirac notation form of the Hamiltonian operator, we have this diagonal form of ket and bra, kk, multiplied by, okay, it's good that you're looking at me and not listening, just recording. K. K factor, K for ket and K for bra. But then it was plus 1/2. And this 1/2 comes from commutation. But what if an operator is equal to a constant? How should we interpret it? We know that any operator is a matrix. And if instead of matrix, someone tells us, Hamiltonian operator equals something plus constant, how do we interpret this constant? What does it mean? How can we represent a constant in form of a matrix? Any ideas?
Identity matrix.
Is it? I agree with you. You're correct. Everyone agrees with Braden, or not quite? So if we set up, I wouldn't say fake. It's a true matrix that doesn't change anything if it is applied on any vector. So if you fill a matrix with ones on the main diagonal, right? And then we construct any vector we have, if you multiply such vector by such matrix, the resulting vector will be equal to original vector, right? So this such matrix will be equivalent to identity, unity, like trivial operation. In form it is matrix, but in fact it changes nothing. If we write it as a matrix, it will be ones on the main diagonal and zeros otherwise. If you write in the Dirac notation, it should be kk. Why do we need it? Because we, okay. How to find expectation value of an operator? You may want to put your operator in a sandwich between your eigen, not necessarily eigen, between the wave function of which you want to find an expectation value. Right now, if you need the energy of the ground state, it means energy, operator of energy, Hamiltonian, and you put sandwich of Brian ket of the ground state wave function. if we would work in the space of continuous Cartesian, then we would use this sombrero Gaussian wave function. On the left and right, they will be the same because it doesn't have complex points. But now we are working in discrete space of the eigenstates. So instead of function, we have vector. And I'm not writing this vector. We use Dirac notation, but it would correspond to the vector with zeros everywhere except the very first element, or element number 0. And we have this vector on the left in form of row, and right instead of in form of vector, and in between we do have the Hamiltonian. Right? Now we have the Hamiltonian in Dirac notation. This frequency of the oscillator 4 times k plus 1/2. So under this 1/2 we should understand the constant 1/2 times identity operator. I was planning to practice calligraphy and write everything down, but it will not work for the day. I mean, don't hesitate. So, send bracket operator, and 1/2 is needs to be replaced by identity operator multiplied by 1/2. If we go forward, this identity operator will be a projector. So, bra, cat, and bra. A thing that will make, will act on vector k and makes vector k again. Do you see any similar terms in these big brackets? Okay, give me a sign if you do not see similar terms inside the brackets. Okay, give me a sign. Either everyone does see or no one cares. Give me a sign if you do see. You can make it secret sign. Give me a sign if you do see similar terms inside the brackets. Okay. Okay. Thank you. What are they? Well, summation sign is the same, and this cat times bra is the same, right? So we can put them outside. And if we put them outside, then inside the brackets, we will have a term that depends on the summation index, on k as an index. So it will be k plus 1/2. Right? What else do we see here? So we see factor up front. We have summation, which we can also put up front. We have this k-dependent factor, or discrete function, and then we can identify our favorite thing, which makes everyone to love quantum mechanics. So that any operator is linear, and any combination that has bra and cat in form of a sandwich in the beginning and the end can be merged into a number. So there will be 2 pairs, bra, cat, which will bring this into, well, we are looking for the energy, right? It is a number. It's not a vector, not an operator. So all strange objects should convolute to a number. And we need to identify do not worry if you see that I'm telling trivial things. Indeed, I do. I'm rolling over things that are known for you, just for kind of refreshment. So we may want to identify pairs of bra and cat vectors that convolute into numbers. Bra, cat, right? Which number will be, if you convolute bra and cat, which represent good basis, basis of normalized eigenstates? If you have two vectors that are represented by, let's say, index k and index another Latin number m, and we convolute bra and cat, which number can we get?
0 or 1.
Everyone agrees, right? So if the I cannot write otherwise I would write your name and plus whatever extra credit. If those Dirac notations represent normalized eigenfunctions, then convolution of bra and cat would be either 0 or 1. If bra and cat are not eigenstates, then it can be anything. But for eigenstates, it is 0, 0, and 1. Well, it cannot be larger than 1, I don't think, even if it is not eigenstates. But here they are eigenstates, and we do see two pairs, 0 and k and 0. So, will it be zeros or ones? So, we should understand this notation as we have summation of infinite number. First term, k equals 0. Second term, k equals 1. Second, third term, k equals 2. So if k equals 0, then bra 0 for ground state overlaps with cat 0 corresponding to ground state, gives 1, right? And same for the second term. Term number 2, bra for ground state, cat k equals 1 for excited state. Their convolution gives 0. Correct. And if you escalate further, all other terms will be 0. So from this summation, only the first term contributes something. The other terms are dropped, right? And if we want to memorize it visually, you can always recall a snake that hunts a mice, right? So the convolution of bra and cat will be represented as delta function, 0, k, and then summation is like a hunter, snake. Factor of frequency, summation, factor that depends on k, and then this stuff that depends on which eigenfunctions we convolute. So drop everything except 0, plug in k equals 0, and keep only 1/2. 1/2 times I h bar omega. What is the energy of ground state of oscillator? I told you. You already know it. And if you, well, I'm telling, do not follow my advice that you will sound in the next 20 seconds. If you want to remember what is the energy of excited state number k of oscillator, immediately start playing with operator algebra. Take this expression and plug the number of your excited state here, And then through operator algebra, you immediately see that is for first excited state is 1/2 plus 1 h bar omega. And for the rest of excited state, you can project. Well, from now on, you can listen. You knew this equation probably from kindergarten or at least from high school, right? H bar omega 1/2 plus n plus k. Energy of eigenstate of harmonic oscillator. Good. Eight minutes. One half, 3 halves, 5 halves. I do not remember the name of the movies, but it is a common scenario in many historical adventures movies when a hero needs to penetrate over the wall in medieval times and throwing an anchor over the wall and then trying to climb. So what we are going to do is throw an anchor over the wall. Over the wall means predict oscillations of oscillator. Well, it's kind of trivial problem to follow, but sometimes, probably next Monday, we will make a great discovery. We will see that oscillator oscillates. But we will be ready. But it will be with very solid background. It's the true oscillator, true oscillates. With all background of quantum theory, and we will be able to expand over simple oscillations. We will be able to answer some questions that Austin did pose and hypothetically answer. So how the uncertainty of oscillator will change. It will be much easier to speak about oscillator after we complete this operation. So inside it's oscillating oscillator, and this anchor is application of annihilation operator to a known state in discrete basis. Why do we follow such strange directions, such strange thing? Should I say I don't know and just promise you colorful results? Well, there is a little background and idea. Remember, in our shortcut scenario, when we were looking for eigenstates, we started from annihilating the vacuum. We applied annihilation operator to the ground state. And this nonsense operation mathematically did help us to form easy differential equation that allowed us to find this sombrero Gaussian shape. We want to discover that oscillator oscillates. But what can oscillate if the eigenstates of the oscillator are, you know what they are? They are multiple nodal points and maxima and minima between the allowed regime. So typically there is no probability much further away from this whiskers of Gaussian shape, well, not Gaussian, quadratic shape. If you have selected energy, if you know the energy of eigenstate, then the eigenfunction fills all the space from left to right where it is allowed regime of motion, and it has oscillations. We went literally only ground first and second, but then you can project. It will be from here to there and several oscillations. What can oscillate there? What is the connection to our intuitive understanding of going forth and back. To go forth and back, and what is the analogy with our common sense classical mechanics where we have position, maybe a little uncertainty, and then we can tell where it is. And on the other hand, if you come to systems where their frequency mass will represent a regime of the classical limit, in such regime where Planck constant is negligible, much bigger than the Planck constant, then indeed we should reproduce classical result where fixed point, certain position oscillates from left to right. So there are two. I'm mumbling some introductory words which, on my view, are not necessary, but maybe they will help you to see some background logic. Although, by going through mathematical operations, you will see it much easier just to analyze the result. So, in case you are seeking for this missed logic, when we were trying to annihilate the vacuum, we saw some minimal uncertainty shape. So maybe if we will try to annihilate something else, again we will come to the shape that will be more or less localized and can oscillate. If you're taking notes, record this saying. Trying to annihilate something, we can come to a shape of minimal uncertainty that would potentially oscillate or something. On the other hand, well, on the previous hand, we will have only two hands, unless we represent octopus. On the other hand, any quantum state oscillator will be a superposition of eigenstates. This is completely not new. This is a standard saying for any quantum theory. But if you would find such quantum state that would have an analogy to classical minimal uncertainty thing, and find how it expands, how one can represent it as a superposition of eigenstates, it will heal us from mental conflict, from counterintuitive things. So if we come up with the shape and we find how it is connected with eigenstates, then we can make this quantum picture intuitive. And our future life in quantum theory, if we have it, will be a little bit more pleasant. Okay. If you are not looking for logic, it's fine. Last 5 minutes were only motivation. As soon as you see the equations when they're done, and it will not be done today, you feel very happy. So any quantum state is superposition of eigenstates, of the eigenstates of harmonic oscillator, in our case. If you step back from chapter of harmonic oscillator, we always can select set of basis states which are normalized or orthogonal to each other and expand any operator, any quantum state in the basis. But right now our basis states are eigenstates of harmonic oscillator. So by setting up set of coefficients in such a way that C sub n absolute value square totally gives 1, normalized to 1, then it will be a general representation of any state of harmonic oscillator. This would work for eigenstate too. If you have only one coefficient equals 1 and the rest are zeros, it will also match this notation. Right? But any superpositional state, when state is combined of more than one eigenstate, will also match this notation. And now we are trying to find to solve eigenvalue problem, which is not standard in a view of basic textbooks. If you look for basic textbooks or in quantum theory as 2 paragraphs or maybe 2 pages in bigger like physical, chemistry, modern physics books, it will be eigenvalue problem only of Hamiltonian operator. But there is no requirement that we need to look only on the eigenvalues of Hamiltonian. We can select any operator and find an eigenvalue. It's not a crime. And now we have kind of promising, not yet solid, but more or less logical prompt that if we find an eigen I realize that I'm pointing on something invisible. If you find eigenvectors and eigenvalues of the annihilation operator, it will make us happy in a sense of discovering that oscillator oscillates. It's so pity that I cannot write here, otherwise I would correct myself immediately. Right now, the eigenvalue doesn't have an index. And the eigenvector doesn't have an index. But in fact, this equation will have infinite number of solutions. There will be infinite number of eigenvectors or eigenfunctions and infinite numbers of eigenvalues. We are going to solve this equation. Just jumping ahead of time, one of these solutions, this eigenvalue 0, will correspond to ground state of oscillator. If we apply it to ground state of oscillator, it will get eigenvalue 0. And we will come to this sombrero shape that we already covered before. But there are other states that are eigen states of annihilation operator, and you will see that they are very, very close to intuitive understanding of the oscillations in the oscillator. And they will be not eigenstates of Hamiltonian. There will be some interesting superposition of eigenstates of our basis functions. The rest are mathematical details. I even can make error in them, but I'll try to start, and even if I do some errors, I will fix them when we meet next time. Okay, 4 minutes. So how do we solve this equation? Again, anytime we try to avoid continuous Cartesian space. We want to do everything in discrete basis of eigenfunctions. It is much quicker and promising in any practical problems. The only exception will be your individual research project. So expansion is coefficients in the basis of eigenstates, and then the operator needs to be represented also, excuse me, as in Dirac form. then from higher it goes to lower. So you just plug it in and identify if there will be any convolution of the brand cat that bring the whole right part to the same object as left part. So it should be the cat. Well, in fact, you see that this bra will convolute with this cat, and this cat will be left. Right? And then we will have left on the right, we will have cat on the left and right. So, iterator, unknown wave function because coefficients are unknown, and we can pull the summation signs to the front. We can pull the index-dependent coefficient also up front, as well as unknown coefficient. And then we see this cat that will survive and convolution of Brand cat that will give the delta function. Okay? And if you carefully follow the protocol of a snake hunting mice, so remove delta function, remove one summation, and then we change the replace one index to another. Then we will get an equation where we do have cat vector on the left and right. Okay. When you have time, I'll come once again through details, but what we need to see, what will follow from this left equals right, that if two vectors are equal, it means that coefficients in front of the same basis functions are equal. Right? And here we will get a connection that expansion coefficient k and k plus 1 are connected. So there will be a recursion relation between these coefficients. So one can solve for all of them. If one knows one, then one can escalate and get the rest. Thank you for waiting for me. Thank you for being here, and looking forward to see you and your homeworks on Wednesday.
Barely, please.